Welcome back to another Chapter 4 physics video where we're looking at solving problems using Newton's laws of motion. So in a previous video we did a pretty simple problem where we had a box that had gravity pulling down on it, and we pulled up with a rope and saw that the box accelerated upwards. So this is a similar problem, but it's made a bit more complicated by the fact that we have two boxes connected with a rope, and a second rope is attached to one of those boxes, and we're going to apply a force. And we're going to see what happens to each of these two boxes as we apply our force on it. So we have to assume, first of all, that the tabletop surface here is frictionless. We will begin to deal with problems with friction later on, but for now we will assume that this is a perfectly frictionless table, and these boxes will just slide across without any friction forces slowing them down. They have masses of 12 kilograms and 10 kilograms, so that's already labeled on the diagram. And we're going to apply a pulling force, F sub P. That's what the P stands for, pulling. A pulling force is applied to the 10 kilogram box. We want to find the acceleration of each box, and then find the tension in this cord. So tension is a type of force. It's basically a pulling force. We want to know what that force is in the rope connecting the two boxes. So when solving a problem with forces, the first thing we should do is draw a free body diagram. So essentially we just need to label and draw all of the forces. So if we look first at this box, we have the pulling force pulling it to the right. The box has weight. It is pushing down against the table, but the table is pushing back with an equal and opposite force, and those two are going to cancel each other out. Then we have the tension. Tension pulls. It's a pulling force, so it's going to pull this box to the left. Okay, so those are all the forces acting on this box. If we look at the other one, it's being pulled also by the tension in the rope. And that may seem a little non-intuitive. How can the force be going in the rope be going in opposite directions? But what you need to remember is that a tension force always pulls. It doesn't push. So it's pulling one box to the right, and it's pulling the other box to the left. It pulls in towards its center in both directions. So this pulling force will be to the right, and again we have the weight of the box acting down on the table, but the table pushes back up with an equal and opposite force, and those two forces cancel each other out. Okay, so if we apply Newton's second law to the first box, Newton's second law can simply be written that the sum of forces equals mass times acceleration. And we're going to treat the vertical and horizontal forces separately. I've already mentioned when creating the free body diagram that the vertical forces are going to cancel each other out. So we have the weight, the normal force, they're equal and opposite, they cancel each other out. There is no acceleration in the vertical direction. The box is not flying off the table or crashing down through the table. It's just sitting on the table. All of the any acceleration that is present is going to be in the horizontal direction. So the sum of forces in the x direction, let's just focus on the x direction, is equal to mass times acceleration. And if we look at the sum of forces, we have the pulling force of 40.0 newtons that we're pulling with, and we have the tension force in the rope. We don't know what that is yet. And that is going to be equal to the mass, which is 10.0 kilograms, times its acceleration, which again we don't know. So we have two unknowns right now. We've got the tension force and the acceleration. And with two unknowns, we can't solve for either one of them using just this equation. We can't arrive at a numerical answer. So I'm just going to leave this equation where it stands. Let's move on to the second box, box B here, the one that has a mass of 12 kilograms. If we apply Newton's second law of motion to it again, we've got sum of forces in the x direction equals mass times acceleration. And so the only horizontal force being applied to this box is the tension in the rope that is pulling it to the right. And so that is equal to its mass, 12.0 kilograms, times acceleration. So again, we have an equation here that has two unknowns. We have the tension force and we have the acceleration. Now, the tension in the rope is going to be pulling this box to the right. It's also pulling to the left with this box, but a tension in a rope is consistent. It's the same. So this tension force is equal to this. It's the same tension force in both equations. And we can imagine that if these two boxes are connected with a rope that doesn't stretch, that if box A accelerates to the right, box B will accelerate at the same rate since they are linked together. So these two acceleration values are the same. So although we can't solve for any one of these variables using just one equation, we now have a pair of equations. We've got a system of equations that we can solve. And so I think what I might do is just use the substitution method. Since this second equation here is already set up for Ft equals, I'll take this and I'll just plug it in to this equation up here for Ft. So that becomes 40.0 newtons minus 12.0 kilograms times acceleration equals 10.0 kilograms times acceleration. And so if I want to get both of my acceleration variables on the same side of the equation, so I'll add 12. It might actually be simpler looking at the algebra to get rid of these units for now. They're just kind of cluttering up our equation right now. Let's get those out of the way so we can focus on the algebra for a moment. So 40 minus 12a equals 10a. So if we get that 12a over to the other side, this becomes 40.0 equals 10 plus 12 is 22.0a, and then a will be equal to 40.0 divided by 22.0, which is 1.82 meters per second squared. So that is the acceleration. The boxes are connected to each other. They're both going to accelerate to the right at the same rate, and their acceleration will be 1.82 meters per second squared. Now the problem statement also asked us to determine what is the tension in the rope. Well, this equation right here says F sub t is equal to 12.0 kilograms times the acceleration, which is 1.82 meters per second squared. So the tension force is equal to 21.8 newtons. So that's the tension in the rope connecting the two boxes. This example problem is somewhat similar to the previous one, with the difference that the cable connecting the two objects is going around this pulley. Around this pulley here. So the tension in the cable throughout a cable is the same. So whatever the tension is here, it will be the same tension here throughout the cable. And what we have here is an elevator car that has a mass of 1,150 kilograms and a counterweight that has a mass of just 1,000 kilograms. So we can see here that the elevator car is heavier, and so it is going to accelerate in the downward direction, and the counterweight is going to accelerate in the upward direction. So we can see that just by observation. What we want to know is, what is that acceleration in meters per second squared? We also want to calculate the tension in the cable, and we have to make some assumptions here. We're going to ignore the mass of the cable itself. We're going to assume that it doesn't affect the masses on either side of the pulley, and that the pulley is frictionless, because friction would slow this down and complicate the problem. So we're going to assume that there is no friction. So first step when solving a problem involving multiple forces is to draw a free body diagram. So we have the elevator, and we have two forces acting on it. We have the weight of the elevator, and weight is equal to mg. And we're going to use the subscript e for the elevator. So m sub e is the mass of the elevator times gravity. So that's acting down. The tension in the cable is pulling it up, Ft. Now we know that the mass is the mass times gravity. The weight is going to be greater than the tension, and the net effect is that the elevator is going to go down. And the counterweight also has its weight. We're going to use c for counterweight. M sub c times gravity is its weight pulling it down. And the tension in the cable is going to be greater than the tension in the counterweight, and it is going to accelerate up. Now we can make the assumption that since they are connected by that cable that goes over the pulley, that at whatever rate the elevator car is accelerating in the downward direction, that will be the same acceleration that the counterweight experiences, but in the upward direction. So we are saying that the acceleration of the elevator equals the negative acceleration of the cable car, and we'll just drop the c subscript for simplicity's sake and just call it a. So if we just refer to the acceleration, then the acceleration of the elevator car is going to be equal, but in opposite direction of the acceleration of the counterweight. I think I'm going to stop right here and resume the rest of this example problem in the next video.